Thanks a lot, and thanks for all of you for being here today with us. I hope so far if this training has been educational and informative to you guys. What I'm going to talk about is about irrigation, and I know a lot of you guys in this room know more about irrigation than I do based on your experience with our irrigated growers, but I want to throw in some of the basic terms and types of irrigation systems, just so that if somebody's not familiar with it, or just to make sure that when we talk about something, we all know what we're talking about. And as Dr. Fox showed you this morning, a lot of the talks that we gave today are on the YouTube channel of the Water Center. It's really easy to remember, youtube.com/user/OKStateWater Center. You see a lot of those videos there, and we'll try to add more to those videos. So it makes it easy to show. Now, again, irrigation systems. So the irrigation is probably one of the most ancient technologies in the world. When it started, when people started growing crops for food, the population was large enough that they needed to do it on an extensive basis. They started with irrigation about 6,000 years ago, and that was the main method for a good chunk of the past 6,000 years. You may hear different people refer to it as flood irrigation or gravity or surface irrigation. It's all referring to the same type of system. It's basically gravity driven. You'll let the water run on the surface of soil down the hill, and it fills the soil profile. Then the sprinkler systems were introduced. We have different types of sprinkler systems, center pivots, linear move, hand move, big guns, you name it. But that's one of the newest advancements, if you consider that multi-thousand years of history. And then we have the drip irrigation system. And you also hear people refer to it with different terms. You hear micro irrigation or localized irrigation. Everybody in the irrigation world has its own opinion and its own favorite. Localized seems to be gaining some popularity, especially because with different types of drip system, the main idea is that you only provide water to a portion of the soil or the root zone, versus with flood or with a sprinkler, you apply water to the entire field. With drip, with micro sprinklers, whatever you have, it's only a part of the root zone. So that's why the term localized is also gaining more popularity. Now, what are the types of irrigation systems we have in Oklahoma? Well, this is from the 2008 data. If you look at it, 84% was sprinkler systems. Only 14 was gravity, and less than 2%, actually, I think this was 1.8% drip system. We have the updated version of this data from 2013. This is the last time that USDA NASS conducted this survey, and these are the numbers. You see a growth in a sprinkler, but that's mainly because we lost a good chunk of our gravity systems that are in southwest corner because of the drought. A lot of the cotton growers could not irrigate in 2013, and that's why you see a larger portion for sprinkler systems. Now, sprinkler systems, the most common type is center pivot system in Oklahoma. Out of that 84%, probably about 95% of it is center pivot type system. And it's called center pivot because it's got a pivot point and it rotates around that pivotal point. So here in this case, and I'm sorry if it's hard to see, but so that's the pivot point. That's where the water is going to the main line. That's the irrigation well, and that's Dr. Fraser, who's going to talk to you about the pump efficiency. And right here he is doing pump water from here. It goes to the pivot point and goes to the main line, and then it rotates. So that's the midpoint of it. This is the other end of it. And as it makes that turn, it creates the circular patterns that you see when you're flying in an airplane. The most common two lengths of the main line is a 1/4 mile and a 1/2 mile system. So these are the two types that you see in this aerial image. Now, center pivot systems have come a long way since they were introduced probably 30, 40 years ago. This is the one of the earliest models. This is California, 1980. In this system, the sprinklers are on top of the main lines. Let's see if the laser works here. So these are the actual sprinklers on top of the main line. So impact the sprinklers like this one, and it shoots water, very high pressure, 60 psi, shoots water into the air. And because of that, a fair portion of water is lost to evaporation, wind drift, things like that. By the time it gets to the ground, you've lost a good chunk of that water. Recent models of center pivot systems, they have drop hoses and nozzles like the one here. So rather than having sprinklers on top of the main line, we have the drop hose and then the nozzles are down here. This is a closer zoom of how the nozzles look like. So you don't see misting. It's very nice, a stream of water, and a big portion of it makes it to the ground. STI is also gaining popularity, especially at the times of drought when water is not available. You can be more efficient with STI, irrigate more acres, but there are some specific things about STI that when folks talk to you about thinking if they want to have STI, you need to know about it, and you need to tell them about these folks. Now, I only have pictures in this slide, so I want you to help me out with what each of these factors are. So, the first one is cost. The STI system costs a lot, much more than center pivot system. Initial cost is a big factor that folks need to consider when they're deciding to go this way or not. There are some companies out there that can do this for lower price, but most of the time they're trying to cut the corners and use a same design that they use for somebody else to try to save on the money and then pass it on to the customers. Filtration system, that's another important thing with drip system, because with drip, unlike the sprinkler, we have those tiny, tiny holes on the drip lines, and the water needs to go through a path to get out of that. So it's very easy for the drip system to get clogged. And if the drip system is under the ground, you won't see it. So you need to make sure that you filter out all the suspended solids out of the water before it's injected into the drip system. Flushing the system, maintenance is really important. So you need to have the filters, but you also need to pay close attention to maintenance. You need to be on top of the system, flush the lines, do all the other things that are required to make sure the drip system stays in good condition. Now, if it's maintained, I've seen drip systems on a commercial scale that are in operation for 20 years, and they're still very good and very uniform. So it has a very high initial cost, but if you maintain it good, it lasts a long time. So this is a blown up version of that path that water needs to go through, and then there's the emitter here. And all the stuff you see here, these are all calcium deposits here that precipitates in the emitters, and in this case, as you can see, it totally clogged up, so you won't get any water out of this emitter. But these are dissolved in the water, so the filters won't be able to filter them out. So that's one of the other things about maintenance. You need to inject acid through the system once in a while to make sure you get rid of all the chemical and biological deposits. What is this one? Chewed up. Some gopher damage. That could be one of the big issues. There are some parts of the country that they have a really bad gopher infestation, and there's just nothing they can do about it. You install the system and it's all chewed up 2 weeks later. So these are some of the issues that folks need to think about when they decide going to STI. But why irrigation is important? So this is an in-service training on groundwater. Why are we talking about irrigation? So let's start with the global scale. On a global scale, 70% of total water withdrawals are for agricultural purposes. That's a big, big portion, because we use a lot of water. Now, the water we use every day, it's not just the water that we drink, it's the water that we eat through the food that we eat. So if you look at the amount of water that we consume, Like, and through the foods, the drinking is 2 to 4 liters, and 4 liters is 1 gallon. If you look at the amount of water that we consume through all the foods that we eat, it's a lot more than that. So these are just some numbers. Like for a piece of a steak, over 2,000 liters, that's like, what, 500 gallons of water for a steak. For apple, you see all those numbers. That's the amount of water that goes into production. I saw an article from California a while ago that every single almond that you eat has consumed 1 gallon of water. So you buy 1 bag of almonds, it's got like, what, 200 almonds in it. That's 200 gallons of water just for that product.
Is that necessarily a bad thing, though? I mean,
no.
Where your water should be going is for food?
Yeah. It's, my point here is irrigation is really a big part of this picture, and we'll talk about Oklahoma too. So if you're thinking about water conservation, this probably should be our first target, because yes, we need to conserve water in cities. We need to take shorter showers. We shouldn't waste water. But all we're doing if we're conserving water here is playing with that 10% of it, while 70% of it is going into ag and to the food production. So that's where the main conservation and efficiency could come from. So if you look at the population projections, it's projected by 2050 we'll have 9 billion people on the planet, and that's on the low side. The most recent estimates are closer to 10 billion people, and they require a lot of food and a lot of water. So we actually need more water to be able to produce all the food they need. And my personal belief is that most of that additional water will come from groundwater resources, and not a whole lot of it will come from surface water resources. So that's how it's important, because irrigation is a big chunk of water consumption, and it relies heavily on groundwater. Now let's look at the situation in Oklahoma. That's the gradient of precipitation for Oklahoma, going from over 50 inches to less than 20 inches on average. This is a slide this chart was in the first presentation too. You look at the crop irrigation, that's like 41% of total water use or water demand in Oklahoma. That was 2007. This is the projection for 2060. It's a little bit less, 36% of the, if you look at the proportion, but if you look at the total amount, it shows an increase, and it's still the largest user of water in the state of Oklahoma. So we're not much different than the global situation with crop irrigation being the largest user. Where's our irrigation water come from in Oklahoma? This is 2008. 83% of that irrigation water is coming from our groundwater resources. And again, that's how groundwater and irrigation are tied to each other. If you look at 2013, it's up to 92%. And this is, again, the impact of drought. People are relying more and more in drought years on groundwater resources when surface water is limited. Map of Oklahoma groundwater major aquifers. You've also seen this. The two aquifers that are used a lot for irrigation are the Ogallala Aquifer, that covers the Panhandle area and this piece of the estate, and the Russia Springs Aquifer here. The rest of them, water is pumped from them for irrigation, but these two are the main two. Now we talk a little bit about the drought and what's the impact of drought, how we rely on groundwater at the drought time, how it helps us when surface water resources are limited. Let me show you some satellite pictures. This is from southwest Oklahoma, Lake Lugert, near city of Altus. This is 1994 satellite imagery. So here's the dam, and it goes all the way up to the north. This is 2000. And this is 2008. That was, I think, the beginning of drought, maybe, or 1 year into the drought. So you don't see a whole lot of change in the lake, in the water area of the lake. And this is 2014. And you can see that the water is here compared to here in 2014. So you see what happened to the water. And because of that, no irrigation water was delivered in 2014. But I'm really interested in satellite imagery, and I wanted to see what is the impact of that when we don't have surface water on actual irrigated agriculture. So I looked at two different areas. This is downstream of Lake Lugert in southwest. So this is one area I looked at, and then this is another area in the Panhandle on top of the Ogallala Aquifer. So I looked at these two areas. Now, this is the satellite image, but I've changed the colors so that the red color represents healthy vegetation. The brighter the red, healthier the vegetation. And here you can see all the center pivots, all the circles here. And that's the green area in the Panhandle. That's 2010. This is 2011. 2010, lots of rainfalls. 2011, very dry year. You see some changes between the 2 years if you look at the pivots, but not a whole lot. Now this is the red area, the southwest area. These are mostly cotton farms, and you hardly see any circular patterns. It's because they're all flood irrigated, surface irrigated. This is again 2010. They received irrigation water from the lake in 2010. This is 2011. You hardly see any red tone, any red shade there. That tells me that nothing was going on in 2011. There was a few folks here and there who had irrigated crops, but basically everybody had to stop irrigating because the lake didn't provide and they didn't have access to groundwater. So this here shows how important is groundwater to the irrigation and to agriculture production, which is one of the main drivers of economy here in Oklahoma. You can also see the impact of that in the acreage of different irrigated crops. If you look at irrigated corn, the acreage even increased over the year. Over these 10-year period, you see the acreage of irrigated corn has increased. But if you look at cotton in 2013, it's less than half of what it was in 2003 and 2008. So they really were hammered hard because they didn't have access to any good quality groundwater resource. So Ogallala Aquifer, the study area, the red study area you saw. This is from USGS, and it shows the decline in groundwater level from pre-development in 1970 to today. And if you look at it, we're here in this area, in the Panhandle area, and you can see we've experienced drops from 25 to about 100 feet in the groundwater level. So we're using that groundwater, especially in drought years, and we're pumping it hard, and it's showing up here because the water levels are dropping. So we're losing that groundwater resource that's down there. This is a time series from one of the observation wells. This is near Texoma, right on the border of Oklahoma and Texas. This shows the same story. So here's the depth to water level. So in January 2011, or 4 years ago, was 228 feet, and now it's about 235 feet. So that's the drop in groundwater level that we've seen over this fairly short period. Notice that all the rains that we received in spring did not make any difference, because as Dr. Fox mentioned this morning, it takes time for that water to percolate down to the groundwater, to the aquifer, and you may have some limiting layers that prevent the water from reaching the groundwater. Now this is an example from Russia Springs. Again, we see the same thing, a fairly significant decline in groundwater level. In this case, because groundwater is much closer to the surface, 50 to 60 feet, we saw a response to all the rains in the spring, but it was not enough to bring it back to where it was 4 years ago. And you can see a start of a decline again as the irrigation season was going on. So we see the impact of that in the data collected by USDA. The average irrigation well capacity in 2013 was 408 gallons per minute. In 2008, it was 505 gallons per minute. And if you talk to growers in the Panhandle area, they can tell you how fast their well capacities have been declining in that part of the world. And that's actually one of the reasons that they're considering subsurface drip, because with drip you don't need those high well capacities. So what can be done? Find new sources of water. Well, good luck with that. It's hard to come up with new sources of water, especially in arid and semi-arid areas. Advanced irrigation systems like SDI. Well, it could help a little bit, but they have their own concerns and considerations. It may not be feasible for everybody to switch to SDI. And use advanced irrigation management techniques. So that's the part I'm focused on, to advanced irrigation management. So regardless of the system that you have, you can improve your management and be able to conserve water. And if you have water, maybe you can use that water on another piece of land, or just save it in the groundwater or in the surface water resources for the dry years. Now, there are the main method the main approach for irrigation management and improving it is to start irrigation before the soil is too dry, so you don't lose the yield, and to stop irrigation before water is lost. Now, most of the time, our growers do a pretty good job with the first part, but when to stop irrigation, we really don't do a good job on that, and that's everywhere in the world you go. So if you think of the root zone of the crops as a glass of water, this is essentially what we do. We want to start adding water before that glass, that root zone area, is all the way empty, and we want to stop before it's all the way full, because if we continue irrigating, we're going to lose water mainly through deep percolation, and because we don't see that, we just don't know that we're losing it, but it's being lost, and with it, it's taking all the fertilizers and all the other valuable chemicals, herbicides, and everything that's been applied to the soil. So what are some of the methods that right now folks in Oklahoma are using to manage their irrigation? Again, this is based on the survey that was conducted in 2013. 88% of the surveyed growers in Oklahoma said they use condition of crop. They go out to the field, they look at the crop, and they decide if it's time to irrigate or not. About 40% of them use some type of feel of soil. And if you are very experienced, they could still work well for you. But look at the use of daily ET, and ET is evapotranspiration, the water use. It's 8%, and that's despite the fact that we have Mesonet with 120 stations all around the state, and despite we have the ET information available to all the growers. But that number is low. Mesonet has some tools. If you go here to their website, there is the irrigation planner, and Al and his colleagues are doing a great job providing the estimates on near real time, and then also putting it into these tools so people can go into it and look at it. So, but again, that number was pretty low despite this. One of the things that I have focused on has been the use of sensors. How can we use soil moisture sensors to find out if that glass of water is near empty or near full, so we can start or stop irrigation? There's lots and lots of different types of soil moisture sensors, and I have examples of several of them here with me that you're more than welcome to come take a look at them. This is one of the things that's a little bit confusing, because if you are someone who's interested in using soil moisture, and this is the type that Mesonet uses, so when you go look at the soil moisture, this is the type of sensor they have. So one of the things, if you are out there a grower, you want to select a sensor, which one you select? Well, cost is important, but which one works better for your condition? So that's one of the things that we are working on to improve. Now I want to give you some examples. So this was a cotton field under center pivot irrigation near Hydro, Oklahoma. So we installed some soil moisture sensors. That's a hole that we drilled so we could install the sensors down the hole. That's the rain gauge that we had, and that's a data logger. These wires are from all the soil moisture sensors that go into the data logger, and it monitors soil moisture. You can set it on hourly basis, daily basis, weekly basis, things like that, and you can go check the numbers. So these are some of the lines, and I know there's lots of lines there and it's a little bit confusing, but basically the vertical bars are either irrigation or precipitation events, and the lines that you see here are soil moisture at 10 inches below the surface, 24 inches, and 36 inches. And the closer the lines are to this top axis, that means the higher moisture content. And you can see this is from mid-July to mid-September this year. You can see as the growing season progresses, we're losing moisture in almost all depth. And you can also see the responses to irrigation. After irrigation or rain events, the estimates go up, show a higher soil moisture because that moisture is being stored in the root zone. So I show this to you because I want you to have a feel of what we can get from these soil moisture sensors, what a grower can expect. There's a ton of information here that they can use to improve their irrigation. They can go here and look at these irrigations and say, well, it created a response in my 10-inch and 24-inch, but it did not create a response in my 36-inch. So this much water that they applied did not make it to 36-inch. They might want that, they may not want that. If they want to make sure they don't have deep percolation, they're doing a good job. And they can tell that. But if they want to get water below the 36-inch, then they know that they can go ahead and adjust the irrigation management. Now just to compare this with the situation we had last year, I have the same graph from the same period last year, and look at the difference in soil moisture. Again, the lower these lines are, it means the root zone is more depleted of soil moisture, it's drier. As you can see, in 2014 it was pretty dry in early August and late August and early September. This year it was a much better condition with all the rains that we received. Same field, the same grower, they can see different years how they can adjust their irrigation practices. This is the same thing for a deficit irrigation treatment. We had a full irrigation 100% and a deficit irrigation, and we're looking at the same thing to see how we can better use the soil moisture. Now I want to talk quickly about groundwater quality. Whenever we have the groundwater irrigation wells to pump groundwater, one of the most important pieces of the system is to have a backflow prevention device on the groundwater, because we don't want whatever we inject into the irrigation system to get back into the groundwater. And this is basically what you can see here. When we started this morning, we had clean water here and the water was moving this way, and I injected some food color into some of these wells, and you can see that the color has moved. So this is basically your pollution. It moved with the water, and we have the color now in this column here and even in the lake that we had here. So that pollution, if it goes back, so we inject fertilizer here, we don't have backflow prevention. If it goes back to the irrigation well, it could move quite a long distance and end up in somebody else's drinking water. So this is 2 injections in time. You can see how they're separated. This injection was when I stopped adding water here, so it basically is spread down here. You can see different things. And it may even end up in the surface water if we're not careful. Now, backflow prevention devices. 2008, 68% of irrigation wells in Oklahoma did not have a backflow prevention device. 2013, 71% of them did not have a backflow prevention device. So still the same situation. This is something that we really need to take serious if we're interested in the quality of groundwater resources. This really needs to be 0, because the type of fertilizers and herbicides and all the chemicals that we inject into the system, we can't allow that to get into the groundwater resources. That ruins the quality, that degrades the quality of groundwater forever. That stays there, and a lot of these compounds don't degrade over time. I also wanted to talk a little bit about salinity. That's another part of the groundwater quality, and it's a two-way solution. In parts of the state, we have high salinity groundwater resources, and folks are pumping. I'm going to go through these quickly. You'll have a copy of this. So people are pumping from saline groundwater resources and using it for irrigation. In other parts of the state, and this is an example of the water test that was done at Dr. Zhang's lab. You see the EC electrical conductivity of 32,000. The EC of Atlantic Ocean is 40,000, so we're not really far from the salinity that you can find in ocean. This is really saline water. Above 2,000, 3,000, we really recommend people not to irrigate, and folks are irrigating with 32,000. So that again has two-way impact. We have folks that are pumping from groundwater, saline groundwater, and applying that to the ground, and that will salinize the soil and cause a lot of issues. But we also have people that are over-irrigating, and there's some salty layers behind their fields, and as the water, the over-irrigation moves through those salty layers, it degrades the quality of the groundwater below the land. So it's another part of the water quality that we need to pay close attention to.